This section's all about differential equations and their applications in the real world. This is really exciting because this is where all the work you've been doing on solving differential equations comes together with situations that you can actually model in the real world. So if we have a look at these two, we've got two of the key results from science that are described by differential equations, and they're Newton's law of cooling and radioactive decay. So Newton's law of cooling is the rate at which a body cools is proportional, and I'm just going to highlight the key things here, proportional to the difference, which means a subtraction, between its temperature and that of its immediate surroundings. And generally the immediate surroundings, we call this ambient temperature. Oops. So if we're looking at the rate of a particular body and how it cools, if we were looking at Newton's law of cooling, we can actually put together a differential equation by using all the information here given to us in the dot point. So the rate at which a body cools, so that would be dt for temperature of an object, dt with time. So it's the rate of change of temperature with respect to time equals, it's what we call, and actually I'll do this on the next line, it's what we call proportional. So proportional, we use a little symbol, sort of looks like an infinity sign without the end closed off. Proportional to the difference between its temperature, so its temperature, and that of its immediate surroundings. Generally we call that Tm for ambient temperature. Okay. Now this particular symbol here, the proportional, means that we're going to rewrite this. We can use an equal sign, but in place of the proportional we use a constant. We multiply by a constant. And because we're looking here at cooling, we usually put a negative in front of this, or you could say the constant is negative, and that multiplies everything that was on the right side. Okay, so that would be an example of a differential equation for Newton's law of cooling. If we were looking at the other example, which is our radioactive decay, and I'll actually solve this one so you can see how this works. You could certainly work at solving Newton's law of cooling as well in a similar way. I'll solve this one because it's a bit easier. I'll do this in blue. If we look at what it says there, it says the rate at which a radioactive substance decays is proportional to the mass of the substance remaining. So again, we're going to do this in a similar sort of method. Okay, so we look at the rate at which a radioactive substance decays is proportional to the mass remaining. So what we could write that as is if we had, I'm just going to say Y is the amount of radioactive substance. So the rate at which Y decays with respect to T, so dy dt, is proportional, so remember that symbol for proportional, to the mass of the substance remaining. So that would be some amount left of Y. Okay. Now what we can do is write that as a differential equation, replace the equal sign, the proportional sign with an equal sign, put a constant, and because we're looking here at decay, I'm going to put a negative constant, and multiply by the right side, which is Y. So we have this differential equation for radioactive decay. Now what we're going to do is try and solve, I'll solve this second equation. So solving dy dt equals negative k y. What we're going to do here is do a bit of separation. So take the dt from underneath, bring it up, and take the y from this side and bring it underneath. What that does is it means that we're going to have dy over y equals negative k dt. And from this point what we can do is integrate both sides. Now this side is the same as 1 over y dy. And k is a constant. So when we integrate this side we'll get log of y. And we're also going to get here negative k, which is a constant, times t plus c. Now I'm going to say here y is an amount of radioactive substance. So let's say that y is greater than 0. So that means that I don't need my modulus signs. To get y on its own, let's raise both sides to the power of e. So we have y equals, and the nice thing about this is we can actually split this up so that we've got this part here, e to the negative kt, and then we also have this part here, e to the c. because you've got a plus in the middle of that exponential, it's the same as taking e to the negative kt and multiplying by e to the c. And because e is a constant, it's of constant value, and c is a constant, this whole thing here, e to the power of c, is also a constant. And the convention for this is to usually call this our initial amount, y0, e to the negative kt. So all we've done is we've just relabeled this part here, the e to the c. So e to the c equals y0. And the reason that that is usually done is because when t equals 0, y equals y0. Because when t equals 0, this whole part here is equal to 1. So this is our initial amount. So that's usually why we subscript that with a little 0. So the solution for this particular radioactive decay problem is this solution here. Y equals the initial amount y0 times e to the negative kt. And the thing that you'll notice, and I'm just going to bring this, bring all of this over. The thing that you'll notice about this is that as k, or as t I should say, gets bigger, this term here becomes smaller and smaller and smaller, and that's because this amount of radioactive substance is decreasing. So it's a negative exponential, so it starts off high and then tapers off like that. So that would be the sort of graph you'd get from this particular equation. So the key here is really knowing a little bit about these two main types of differential equations. Radioactive decay is a really important one. It does get used quite often, and also Newton's law of cooling. So those two differential equations, pretty much just being able to construct a DE from a word problem as well. So the key thing here being proportional, meaning that we have whatever is proportional is going to be multiplied by a constant, and because it's decreasing we put a negative, and then being able to solve your differential equation by separating out your, in this case, t's and y's, integrating both sides and then simplifying to get a differential equation solution which is in a nice simple form. So that's the key to applications of differential equations.